Hi, and welcome to the Getting Started video on writing and querying data for the DataStax distribution of Apache Cassandra. In this video, we'll be going through some of the different write and query operations that are available with Cassandra Query Language, or CQL. In previous videos, we learned how to connect to your cluster and set up a key space. We've also created two tables that will store data for our application, one called Videos and another called Latest Videos. Let's take a look at some useful commands that you can use to see what key spaces or tables exist in a Cassandra cluster. The Describe Key Spaces command will show you all of the key spaces that exist in the database. Besides the killer video key space, the rest of the key spaces here are automatically generated by the database, and you most likely won't need to do anything about them. The next command is Describe Key Space, without the S. If you specify a key space name, this command shows you the schema definition for both the key space, the tables, and the other database objects within the key space. Here you can see the key space definition for killer video, and the table definitions for videos and latest videos. Next is the Describe Tables command, which gives you all of the tables in each schema. If you set a default key space like what I'm doing here, then Describe Tables will only list the tables within that key space. Finally, the Describe Table command with a table name displays the corresponding table definition. Okay, now that we are familiar with the tables we've created, let's start by adding some data. The write operations we will look at are the insert operation, the update operation, and the delete operation. If you are familiar with the structured query language, SQL, you will find these operations to be intuitive. The insert operation uses the insert into keywords, followed by the table name, and then, in parentheses, add the column name for the corresponding data. At a minimum, this needs to include all of the primary key columns. For the case of the videos table here, that means we would need to include the video ID column. Here, I'm only going to include the video ID, added date, and name column. Cassandra has a sparse storage engine, so all of the other table columns that you don't specify will not take up any space. So don't worry if there isn't data for every column in the row you are inserting. Next, I use the values keyword and then add values for the columns. Since the video ID is a UUID column, I'll need to add a 128-bit UUID value like this. It can be hard to remember the exact formatting for a UUID, but CQL does have a function named UUID that can automatically generate a UUID. If it is a time column, we use the now function instead to generate a time UUID value. Note that, in CQL, strings are enclosed in single quotes. Our added date column is a timestamp column, but you can insert the value as a string, formatted as ISO 8601 or as a Unix timestamp integer. With a string similar to the one I'm using here, Cassandra will truncate the smaller units like hours, minutes, and seconds. Okay, that's an insert command in a nutshell. Let's turn our attention to an update command. Here we have the update keyword in the table name we want to update, followed by the column name and the value that we want to set. Then we need to specify the row we are updating by including a where clause that includes all the primary key columns. We'll set this to the video ID value that we have just inserted. The last write operation is the delete operation. We use this to delete rows or delete individual columns within a row. For this example, we will delete a single column named Location from our recently inserted and updated row. Note that if we wanted to delete the entire row, we can just write Delete From. I'll add a few more writes here to populate our table, so feel free to follow along. Okay, now that we've written the data, let's see how to query the data. We begin with the select keyword followed by the specification of rows we want to retrieve. Just like SQL, the column specification can either be star, which retrieves all of the columns, or we can enumerate the individual column names we want. Next, we add a from clause to identify the target table, in this case, videos. Now, if we end the statement like so, this would cause a full table scan that would retrieve all of the rows in the table. This may not be bad right now since we only have a few rows, but in a production system where you might have millions of rows, this type of a query would not be performant. Instead, let's add a where clause here to specify the video ID, which is the partition key column. This retrieves only the row whose video ID value matches the specified UUID value. If you are querying a table that has both a partition key and clustering columns, then it is possible to retrieve multiple rows, like this query here. You'll notice that the results come back in sorted order based on the added date column, since added date is a clustering column. While I've said that you may primarily query data using just the partition key, it is possible to include the other columns in the primary key as well. You don't have to specify all clustering columns, but if you do specify a clustering column, you must also include the specification for all clustering columns that precede the clustering column of interest. For example, let's say that we want to retrieve only a specific row in the latest videos table. We have to provide a value for the partition key, but why not just add a condition for the video ID? As you can see, this query results in an error since the query does not include the added date column in the where clause. If we add in the remaining clustering column added date, the query succeeds and we get back the resulting row. The query here works fine since both YYYYMMDD and the added date columns are the leftmost columns of the primary key. There are some things you can do to modify the results of a query. You can set an order by clause to change the sorted order of the clustering column. You can also set a limit to limit the number of results the query returns. If you have experience with SQL, CQL writes and queries should feel intuitive. However, there are many things that Cassandra is doing under the covers that helps these operations to be performant, and it is a good idea to know a little bit about how Cassandra works. One important concept is the way writes work in Cassandra. CQL differentiates inserts, updates, and deletes, but in the end, Cassandra handles all these mutation operations in a similar manner. This means that you can actually use an insert operation to update an existing row and an update operation to insert a new row. Cassandra does not check if there is an existing row with the same primary key values before doing an insert or an update. Here we execute two insert operations that use the same video ID value. There is no error with the second insert. Instead, if we look at the resulting row, we see that the second insert has overwritten the previous column's values and has added values to the columns that previously did not exist in the row. We call this behavior an upsert. It's because of this special property of Cassandra writes that we stress the importance of designing your table primary key properly. If the primary key does not ensure uniqueness, then it is possible for new inserts to overwrite existing rows with no warning or notification. One last thing I want to discuss is the way deletes work in Cassandra. Rather than physically removing data when executing a delete, Cassandra writes a record called a tombstone, which indicates that the corresponding data is no longer valid and should be ignored during queries. This method serves two purposes. First, it makes deletes just as fast as an insert or update. And second, the tombstone serves as a marker when syncing data across different replica sets. Eventually in the background, Cassandra will remove the deleted records along with the tombstones, but this may happen several days after the delete. If an application's write pattern contains too many deletes, this may lead to a problem. Too many tombstones can accumulate and significantly slow query execution, since Cassandra must read through all these tombstones as well as the actual live data. Some of the topics in this video are complex. If you would like to learn more, you can check out DataStax Academy at academy.datastax.com, where we offer free training courses that cover these topics in more detail. Some other topics you may be interested in include bulk loading data, performing range scan queries, lightweight transactions, the Cassandra write path and read path, and compactions. The content on DataStax Academy is very helpful, and it's all free.